Hi, my name is Dmitry Itsykson, and I am presenting our joint work with Aleksander Knop, Supercritical Tradeoff between size and depth resolution of parities. This is a paper on propositional proof complexity, and I will start with a short introduction. The main object of study is a propositional proof system for language L. Namely, we prove that a given string x belongs to the language L. A proof system is a polynomial algorithm that verifies proof. The proof system is called polynomially bounded if for any string x and L there exists a proof of polynomial size. The set of languages having polynomially bounded proof system is also known as a class NP. A propositional proof system is a proof system for the language unsat which consists of unsatisfiable formulas in conjunctive number form. It's easy to see that the classes NP and co-NP are different if and only if propositional proof system has a family of hard formulas that do not have short proofs. The main program in proof complexity is so-called Cook's program of proving superpolynomial lower bounds on proof sizes for particular proof systems. The ultimate goal is to understand the reason why NP and co-NP are different. Let us consider particular examples of proof systems that are important for our work. First of all, I give the definition of the well-known resolution proof system, but I do it in a top-down way using the notion of a decision deck. To show that a formula is unsatisfiable, we split on the value of variable. Namely, we have a deck with one source where our degree of internal nodes is 2. Every node is labeled by a partial assignment. The source is labeled by the empty assignment. At every node, we split on the value of a variable. One of outgoing edges is labeled with equation this variable equals 0, and other this variable is equals 1. If there is an edge between two nodes, the assignment on the first node plus equation on the edge implies the assignment on the second node. For every sink, the assignment of the sink falsifies some clause of initial formula. The size of the refutation is the number of nodes. The resolution size of the formula is the size of the shortest refutation. The depth of refutation is the length of the longest path from the source to a sink. Resolution depth of the formula is the minimum possible depth among all refutations. There is also a very important parameter, the width of refutation. It is the maximum size of the assignment over all nodes. The resolution width of the formula is the minimum possible width over all refutations. The second proof system we consider is resolution of parities, and we defined it via parity decision deck. The difference from the previous definition is that we now split on the values of F2 linear forms. And we have linear system over F2 in nodes instead of assignments. The local condition is the same if there is an edge between two nodes, then the linear system on the first node plus linear equation of the node on the edge implies linear system on the second node. For every sink, the linear system within it contradicts to some clause of refuted formula. Size and depth are defined in a similar way as for resolution. Lower bounds for resolution have been known for quite a long time. One of the first lower bounds is the result of Urquhart, which states that the CNF encoding of F2 linear system based on expanded graph requires exponential resolution proofs. There is a huge amount of lower bounds results for resolution, so I will mention only several of them. The theorem of Benson-Wigderson states that if a formula has a large resolution width, then it also has large resolution size. Therefore, resolution width is a very important parameter. In a joint paper with Dmitry, we showed that F2 linear systems encoded in CNF are easy even for tree-like resolution of parities. That is the case when the deck is actually a tree. A major open question is to prove a superpolynomial lower bound for resolution of a parity in the general case. Resolution of a parities is a subsystem of bounded Frege with parity gates, and it is the simplest subsystem of the later proof system for which we still do not know how to prove size lower bounds. So establishing lower bounds for resolution of a parity is an important step toward the harder question of establishing lower bound for bounded Frege with parity gates. Lower bounds are not known in the general case, but they are known in the tree-like case. I will only mention one of the results, which is based on lifting. Lifting is a technique allowing one to derive lower bounds for a stronger model from lower bounds in a weaker model. A A hard instance is usually obtained by composition. In proof complexity setting, we have a CNA formula phi with variables y1, y2, ym. We have a Boolean function g that maps L bits to 1 bit, which we refer to as a gadget. The lifted formula phi composed with g is obtained by the following process. For every variable yi, we substitute g with L fresh variables xy1, xy2, etc., xyl, and convert the resulting formula to CNF. In order to control the size of the formula, we usually consider all the small gadgets where L is constant or logarithmic. Chattopadhyay, Mandelsanyal, and Sharif define the notion of k-stifling gadget. It is defined as follows. For any k variables and any Boolean value a, we can fix the value of other L-k variables such that the value of the gadget will be fixed to a regardless of the value of unfixed k variables. The main examples of k-stifling gadget is majority of 2k plus 1 bits. It's easy to see that we can fix the remaining k plus 1 variables to a and fix the value of majority to a. The result of Chattopadhyay, Mandelsanyal, and Sharif states that one can lift from resolution depth to tree-like size in resolution of the parities. Namely, the size of any tree-like resolution parity refutation of a formula lifted by a k-stifling gadget is exponential in the resolution depth of this formula times k. It's easy to prove lower bounds. It's rather easy to prove lower bounds resolution depth, since it's simply the query complexity for the search problem of finding falsified clause given an assignment of an insatisfiable formula. In the DEG-like case, there is a progress regarding bounded data resolution of parity reputations. Namely, the following results was obtained in our paper with Yaroslav Alekseyev. I present it here with a small improvement obtained with Klimi Fremenko. There exists a family of formulas phi sub n with n variables such that any resolution of a parity refutation of phi sub n either has exponential size or depth at least n log n, where n is the number of variable. The hard formula here is the staging formula of a logarithmic degree expander lifted by majority 5 gadget. The natural question is whether this formula actually has a short refutation, but superlinear depth, or it doesn't have short refutation at all. The main question addressed in our paper is the following. Does there exist a formula that admits a short resolution of a parity refutation, yet any such refutation must have superlinear in the number of variables depth? A negative answer to this question will apply a superpolynomial lower bound on the size of resolution of the parity refutations. And the positive answer will establish a supercritical trade-off between size and depth. Let us explain what we mean by a supercritical trade-off. Consider a plot where on the x-axis we have depth and on y-axis we have size. There is a worst case upper bound n on depth and 2 to the n on size. A plane trade-off usually states that we cannot optimize both parameters simultaneously. For some instances, depth is small but size is close to its worst case upper bound, and for other instances, size is small but depth is close to its worst case upper bound. For a supercritical trade-off, the situation is different. For some instances, the size is close to its worst case upper bound, and for other instances, size is small, but depth exceeds its worst case upper bound. This is why it is called supercritical. There are known supercritical trade-offs in proof complexity. I will mention only result concerning the proof system we are talking about. Razborov established a supercritical trade-off between width and size for tree-like resolution. Chattopadhyay and Dvorak lifted this result to tree-like resolution of the parities. Fleming, Petassi, and Robert, and then, using a slightly different technique, Bass and Tapin, established supercritical trade-offs between width and depth and between size and depth for resolution. Now we are ready to state our results. Assume that any resolution refutation of formula psi has either width at least w or depth at least a square times w. Then, any resolution of the parity refutation of the formula psi lifted by the composition of parity of size s and majority of size 5 has either size at least to the w, or depth at least omega of s squared times w. If we start with a formula that requires resolution width at least w, then we can ignore the depth condition and obtain simply lifting for resolution width. We combine our result with the supercritical trade-off by Bass and Tapping. Namely, they constructed a family of formulas psi sub n with n variables in O log n CNF that have polynomial size resolution refutation, but any resolution refutation requires either width at least n over log n or almost quadratic depth. As a result, we get a supercritical trade-off, a family of formula psi n with n variables that have quasi-polynomial resolution refutation, such that any of their resolution of a parity refutation have either exponential size or superlinear depth. Notice that this is the first example of such supercritical trade-off that holds for a proof system without superpolynomial size lower bounds. If we combine our theorem with the trade-off by Bass and Tapping using different parameters, we get that resolution of the parities is strictly stronger than its fragment that allows only refutation of depths at most n to the 3 over 4 minus epsilon for every positive constant epsilon. In the rest of the talk, I will present an outline of the proof. We start with the notion of closure of a set of linear forms. We are in the lifting settings. We have unlifted variables y1, y2, etc. ym, and lifted variables xij when I is from 1 to m and j is from 1 to l. Let j be one Staffing gadget, and for every assignment of lifted variables by gadget g, induce an assignment on unlifted variables by essential way. Consider a set of linear forms f of the lifted variables. Let I be a set of unlifted variables. We say that f does not restrict I if for every satisfiable linear system phi with a set of linear forms f and any solution of phi, the following holds. If we take this solution and the assignment on unlifted variables induced by this solution, and then modify the values of variables from I, somehow, we can find another solution of phi that induces this modification. The paper by Garlick, Framing, and myself proved the following theorem, which states that there exists a mapping from the set of linear forms over lifted variables to the set of unlifted variables. This mapping is called the closure, and its informal meaning is to indicate the closure indicates the most essential unlifted variables for a given set of linear forms. It has the following properties. First, f does not restrict the values out of the closure, unlifted variables out of the closure. The second, the empty set does not have essential variables. If we increase the set of linear forms, the set of essential variables does not decrease. If f and g has the same span, then they have the same set of essential variables. And the size of the set of essential variables is at most the dimension of the set of linear forms. Okay, let phi be an satisfiable formula and A be the set of assignments of its variables. We say that A is proper if no assignments from A falsifies the clause of phi, and every sub-assignment of an assignment from A is also in A. Let phi be a linear system over lifted variables. We say that phi is A good if phi has a solution that induces on the closure of its set of linear forms an assignment from A. We will use the following two properties of a good linear system. First, if phi is A good, and then phi does not contradict any clause of the lifted formula. This follows from the fact that element of A do not contradict clauses of the unlifted formula, and in the solutions we can modify values outside of the closure as we like. And second, if a linear system phi semantically implies psi and psi is A good, then psi is also A good. Indeed, if phi is satisfiable, hence semantical implication means that every equation of psi is a linear combination of equation of phi. Then the set of linear forms of psi lies in the span of the set of linear forms of phi, and thus the closure of linear forms of psi is a subset of the closure of linear forms of phi. Now it is straightforward that the solution of phi can also be used as a solution of psi, and its restriction to the smaller closure is also an A. Okay. Consider formula phi and the proper set of assignments A. We say that A is WS nice if it is additional has two properties. First, if rho from A and the size of rho is less than WS, then for every variable x, we can prolong rho to the variable to the value of x such that the resulting assignment is also an A. Second, for every chain of assignments from A, where each following assignment extends previous by one variable, the number of cases then the extension is forced does not exceed W. By forced extension, I mean that the assignment cannot be prolonged with the opposite value of the variable. A theorem that is actually proved in another paper by Aleksander and myself, we showed that phi has WS nice set of assignment, then any resolution of the Parities refutation of phi lifted by the majority phi of size at most 2 to the W has that at least omega of WS square. Let us present an outline of the proof of that theorem. The method is called random walk with restarts. Consider a parity decision deck of the lifted formula. We assume that its size is at most 2 to the W, and our goal is to prove a lower bound on the depth. We consider random full assignment of lifted variable sigma. Then we consider path P from the source of the deck of length WS over 2. Each time we traverse an edge, we ensure that the equation written on that edge is satisfied by sigma. Let psi P denote the linear system written on the edge of P. I claim that psi P is a good with probability at least 2 to the minus 4 times W. I will not give formal proof of this step, and I will try to explain it. During the path, the size of the closure of psi P increases from 0 to WS over 2. If we substitute random assignment for the unlifted variables, the probability that the assignment to the closure is from A will be at least 2 to the minus W by the properties of WS nice assignments, as there are at most W forced values. But since we have a different distribution, we pay a constant factor 4 in the exponent. Let S be the set of nodes V that are ends of paths of length WS over 2 from the source such that the linear systems in those nodes are A good. Let V1 be a node from S such that rank of phi V1 is minimal. We know that the probability that psi P is good is at least 2 to the minus 4W. This probability is at most the probability that phi P is good, where phi P is a linear system at the end of the path P. This is because by the property of the parity decision deck, phi P is semantically implied by psi P. Furthermore, this is at most the sum of all V in S of probabilities that sigma satisfies phi V1. Since sigma satisfies all linear system along the path by construction, the probability that a random assignment satisfies a given linear system is at most 2 to the minus rank of the system. Thus, the sum is estimated as 2 to the W, as the deck contains at most this number of nodes, times 2 to the minus rank of phi V1. Hence, the rank of phi V1 is at most 5W, and thus the size of the closure of phi V1 is also at most 5W. And Y1 is deeper than the source on the distant WS over the 2. Then we execute a second random walk starting from V1 using a random solution of the system phi V sub 1 and another WS over 2 steps. We will reach a node V2 that is deeper by WS over 2 steps such that phi V2 is also a good and its closure is smooth now 10W. We repeat this S over 10 times until the size of the closure reaches WS over 2. Finally, we get a total depth of S times 10 times WS over 2, which is omega of WS squared. Okay, now let us discuss how to obtain WS nice sets. Itsykson and Dalmau presented the following characterization of the fact that a formula phi has a resolution refutation with at least W. It is equivalent to the existence of a non-empty set of proper assignments called W being position, such that any assignments of size less than W can be extended to include any variable. This notion is close to the notion of WS nice sets, but we also have to bound the number of forced decisions in the chains. This can be done by lifting using the parity gate of size S. Namely, it is possible to prove the following lemma. If phi requires resolution proof of width at least W, then phi, lifted by a parity of size S, has a WS nice set of assignments. The idea is that among S copies of every variable, the first S minus 1 values are not important. It is only important to choose the correct value of the last copy to fix the whole parity in the appropriate way. Now we have the lifting from resolution widths. It is not too bad, but it is not sufficient for the trade-off since lifted formulas with large resolution widths are likely hard, and we will not be able to prove an upper bound. Thus, we will try to relax the notion of WS nice sets. Specifically, we relax the property that a subassignment of an assignment from A must be also in A. Let's see what we actually need in the random walk with restart argument. We start from the empty assignment and repeat S over 10 times the following. We extend row by at most WS over 2 variables and then restrict row to its subassignment. We only need to ensure that during such operations, row doesn't leave A. Such a property can be achieved by assuming a weaker condition on the initial formula. Namely, assume that any resolution refutation of phi either has width at least W or depth at least WS squared. Then phi lifted with a parity of size S has this almost WS nice set of assignments. This lemma, together with random walk with restart argument, implies our theorem. Specifically, if any resolution refutation of psi has either width at least W or depth at least W squared, then any resolution of a parity refutation of psi lifted by the composition of parity of size S and majority 5 must have either size at least to W or depth at least omega of WS squared. There are several new results that have appeared since our paper involving the since our paper appeared involving the depth bound, improving the depth bound. All these results also obtained via random walk with restarts method. First, Bachatarai and Chattopadhyay proved that the Itsykson formula lifted by the IP gadget over log n bits requires resolution of the parity refutation of size at least to the n to the epsilon, or depth at least n to the 2 minus epsilon. Then Bayramji and Palyatser proved the same trade-off for the binary pigeonhole principle, a formula with a clear combinatoric meaning, and also for the lifted Itsykson formula with a one-stifling gadget. The second example is interesting because the depth is superlinear in terms of the size of the formula and not only in the number of variables. And the natural open question is to prove a truly supercritical trade-off between size and depth for resolution of the parity, in which the depth is superlinear with respect to the size of the formula. That is all. Thank you for your attention.